Hello, AP Physics 1 students. Let's start by reviewing what we did here in problem 10. So we combined the ideas of the inclined plane with friction. Drawing a free body diagram, we got weight pointing straight down, normal force up on the angle, and this object is sliding down a rough incline, which means if it's moving down the incline, friction, which always opposes relative motion, is impeding the motion by pointing up the incline. Doing our usual resolution of the force of gravity into its components down the incline and into the incline yields that mg sine theta points down the incline, mg cosine theta points into the incline, which is going to happen every single time. You never have to do the fun game of find theta again. Mg sine theta will always pull the object down the incline. Mg cosine theta will always press the object against the incline. And in this situation, the normal force is just balancing out mg cosine theta like it was on the frictionless incline. Doing sigma F equals ma down the incline yields mg sine theta minus force of friction, and then combining the force of friction equation for the kinetic force of friction with the normal force of mg cosine theta and canceling out the mass yields this interesting result here that we saw that even if it weren't a rough incline, if mu sub k equals 0, provides the usual a equals g sine theta. And now we take it to the next level here of problem 11, where we say, okay, what if we put this object on the incline and friction is actually enough to hold the block in place? So I want you to pause the video, draw the entire free body diagram of the block, and see if you can at least start the solution to this. So hopefully you realize the free body diagram is no different than it was in problem 10. We're going to have weight pointing straight down, normal force up on the angle, friction pointing up the incline. The object is not moving down the incline, but it wants to move down the incline. It should move down the incline, and friction is the force preventing that from happening. So the friction is going to point up the incline, holding this block back from sliding down the incline. Now at this point, if you want to resolve the force of gravity to its components, you certainly can, but hopefully you're starting to get a sense of what that looks like, and you can just look back at the free body diagram back from problem 10, and if you want to do it, that's great, or maybe you can just mentally picture that mg sine theta is pulling it down the incline, mg cosine theta is pushing it into the incline. And in this situation, the block is not moving. So of course the velocity is 0. The acceleration is 0. The net force is 0. Right. So what's holding it back? Well, it's the force of friction. What's trying to pull it down the incline is mg sine theta. And so if it's not accelerating down the incline, what do you know about those two forces? Right. They have to sum up to 0. And so in this case, mg sine theta is balanced by the force of friction, whereas in the previous problem, mg sine theta was winning as it went down the incline. So we start from this idea that the component of the force of gravity trying to pull it down the incline is exactly balanced by the force of friction, which means what kind of friction is it? Right, it's static friction. What's our equation, or inequality for the force of friction? Well, remember, this is where it's that whole range of values from 0 up to and including some maximum amount. Force of friction is less than or equal to mu sub s n. This idea of the inequality means we're going to be able to get a range of values that's going to allow the force of friction to prevent this block from sliding. So what we can do is we can just drop mg sine theta in for force of friction. So we have this, mg sine theta is less than or equal to mu sub s n. And we want to try to get this in the simplest terms possible. What do we know about the normal force in such a situation? What is it equal to? Yeah, we don't have to do the whole resolve the force of gravity into its components, do a two-dimensional chart. We should be able to see that the normal force is just balancing out this component of the force of gravity, which is given by mg cosine theta, just like it has been in all these other incline problems. So, drop this equation for normal force into this equation, see what happens, and see if you can do the algebra yourself to solve for a condition for theta. You're basically trying to solve for theta. Pause the video and try it on your own. Alright, it's really not that difficult. We drop normal force in for mg cosine theta in for normal force. And then we see, what can we do to simplify this? We've got mass on both sides and g on both sides. So they cancel. This is going to be a condition that's completely independent of what mass of the block is on the incline, and it's independent of what planet you're on. As long as there's gravity trying to pull the object down the incline, it doesn't matter what the value of g is. You should also be able to see that if we're solving for theta, we can divide both sides by cosine theta, and you should remember the trig identity, sine over cosine, is equal to tangent. So now we're up to this. Tangent of theta is less than or equal to mu sub s, and I tasked you with trying to solve this for theta. So what do? Right, we take the inverse tangent of both sides. And so here's what we've got. that theta is less than or equal to the inverse tangent of mu sub s, meaning that this is going to give a range of angles that is completely dependent on just one thing, the properties of the incline itself. So you can sort of imagine an inclined plane that's hinged over here. So maybe it starts level with theta equals 0, and you can raise it up and raise it up and raise it up, increasing that angle. And for a range of angles, the force of friction will be enough to hold it in place, exactly matching the value of mg sine theta, up to and including some maximum value given by this inverse tangent of mu sub s. And when it's at that largest value, friction is just barely holding on, this static friction force. Anything beyond that, and friction will just not be enough to prevent it from sliding, mg sine theta will win, and it will slide down the incline. So notice I put a dashed line around this, indicating it's like a semi-new equation, a quasi-new equation, because it's very, very limited in its scope. What does this equation actually get us? Well, theta here is the range of angles for which friction can hold an object at rest on an incline. That's a lot of words. And the more words we have, the more specific this equation is. This is a very limited equation. It's a great equation. It's a very important equation. Like if you are an engineer designing ramps and things like that, and you want to make sure things don't slide on the ramp, well, this equation is what you need. But it does one thing and one thing only. It only gets this range of angles that will allow friction to prevent an object from sliding down an incline. So it's a great equation, but it's very limited. So if you are going to use this, if you're going to put this equation on your list of new equations, you certainly can. If you're going to put it on your cheat sheet, well, they strongly suggest that you write all these words describing when you can use this equation, when you can't. Because if you try to use this equation in any other situation, it's actually completely useless. So you just have to know when you can use it and when you can't.